In example 3, we have a police cruiser approaching a right-angled intersection from the north, and he's chasing a speeding car that has turned the corner and is now moving straight east. So we need to draw a picture of the situation that we just described. So you've got the police cruiser here traveling toward the intersection. The car that it's chasing has already turned the corner and going east. Police cruiser is coming from the north, and the car is traveling east. So we've shown this situation. It says when the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with the radar that the distance between them and the car is increasing at 20 miles per hour. So we need to represent the distance between them. That would be, let's call it Z, and we're going to call the distance that the police cruiser is from the intersection Y and the distance that the car is from the intersection X. Now, you might be tempted, and a lot of kids are when they first learn this, they might be tempted to put in a 0.6 here and a 0.8 here, but you can't do that because they are not constants. One of the big things we tried to stress at the beginning is you cannot put numbers into your equation or into even the picture until you determine that it's a constant, and it's not, because this cruiser is only 0.6 miles north of the intersection at an instant. It's moving. So the distance between the police cruiser and the intersection is changing, as is the distance the car from the intersection is changing. So you can't put numbers there. You can't put any numbers in this picture because all these numbers are changing. And the distance between the police car and the cruiser is also changing. So we've got that in our picture now. And now we need to determine, okay, what are we trying to find? So what are we trying to find? Well, let's read the rest of the problem. So as we look at the rest of the problem, it says the police determine with the radar distance between them and the car is increasing at 20 miles an hour. If the cruiser is moving at 60 miles an hour at the instant of measurement, what is the speed of the car? So if we were looking for the speed of the car, that means we're trying to find dx dt. All right, so we're trying to find dx dt. And when, at what instant of time are we trying to find that? That's important. And we're trying to find it when the cruiser is 0.6 miles north. So that means when y equals 0.6. And then the car is 0.8 miles to the east. So that means x is equal to 0.8. So that's when we're trying to find it. But they also determine at that instant with radar that the distance between them and the car is increasing at 20 miles an hour. So that means we also know that dz dt is equal to 20 miles per hour. And it's told also that if the cruiser is moving at 60 miles per hour at the instant of measurement, so now we also know that dy dt is going to equal 60, but it's not 60, it's negative 60 miles per hour. And you might say, well, what do you mean negative 60 miles per hour? Well, that's because the cruiser, the distance between the police cruiser and the intersection is decreasing. And if you recall, when we did velocity things earlier this year, we said if the velocity, if that distance was decreasing, it's going to have a negative velocity. And so that's the case here with dy dt. All right, well, I think we've written down everything that they told us. Now we've got to come up with an equation to relate the rates of dy dt, dx dt, and dz dt. And that's a pretty simple thing because you have a right triangle. And we know that x squared plus y squared is equal to z squared. All right, so now we're simply going to take the derivative. And that's going to be 2x chain rule dx dt. Remember, we're taking the derivative with respect to time. And so then it'll be plus 2y times dy dt, chain rule, equals 2z times dz dt. And so now I've written an equation that relates all the rates, and now it's time to plug in all the things that I know. So this will be 2 times x, and we know that x is 0.8 at the instance of measurements. dx dt is what we're trying to find, so that'll stay there the same. And then plus 2 times y, and we're trying to find that when y is 0.6. We're trying to find the information when y is 0.6, and dy dt, we're told, is negative 60. And that equals 2 times z. And now we say, well, wait a second, nobody told us what z was. But you can figure it out, can't you? Because if x is 0.8 and y is 0.6, 0.8 squared plus 0.6 squared is going to equal z squared. And of course, if you remember, 6, 8, 10 is a triangle. That means z is going to be equal to 1.0. All right? And if you needed a calculator, you could go and figure that out too. But it's a 6, 8, 10 triangle, so it's 0.6, 0.8, and then 1.0. So that means z is going to be 1. And then dz dt, they told us, was 20. So the only thing left, I only have one variable left, dx dt. That's wonderful. So now I've got, this is going to be 1.6 dx dt plus 2 times 0.6 times negative 60 is going to be negative 72. And that's going to equal 2 times 20 is 40. 1.6 dx dt is going to equal 112 when you add 72 to 40. And dx dt, which is what I'm trying to find, if I take 112 divided by 1.6, it comes out to be 70. That's 70 miles per hour. That is the speed of the car trying to get away from the police car. So we answer the question, and we, as always, have to state a sentence. At the instant of measurement, that's when x is 0.8 and y is 0.6, the speed of the car is 70 miles per hour.